And Savas Gider was born in Greece and studied physics at Cornell and UC Santa Barbara. After as a postdoc at IBM, Almaden, and he worked for many years on hard disk drivers at IBM and Toshiba and Western Digital. And he still works on magnetics as a part of the motion sensing group at Apple. But he always wanted to be an astronaut. Okay, Savas, we can start. Thank you very much for your talk. And please, we can start. Yeah.
Okay. Thanks for inviting me. Thanks for the introduction too. Probably many of you know, like about 2 years ago was the 50th anniversary of the first moon landing. And at that time, there were a lot of stories about it. And in one of them, I heard about the navigation system. And I'd actually never thought about that. How do they actually get there and back, right? And so that led me to look into some more details. And I was surprised, that they used motion sensors, which is one thing I work on now. So probably everyone has seen this picture. Most people.
Savas, you need to share your presentation.
Oh, sorry. I thought I had already shared it. Now, can you see it?
Perfect.
Oh, sorry. Okay. Probably all of you have seen this picture before. Most people would guess that it's Neil Armstrong, but it's actually Buzz Aldrin. You can see Neil Armstrong reflected in Buzz's helmet there. What's maybe you've never noticed before is there's actually a navigation device somewhere in this picture, and I'll explain it at the end. Okay, I'm gonna go down. Okay, now it's trapped. I can't seem to advance. Oh, there we go. Okay. All right. So first I wanted to comment just on the magnitude of the Apollo program. When people think of a large program, one of the ones that might come to mind is the Manhattan Project. But actually, when you compare it with the Apollo program, the scale is not even close, right? By almost every measure, right, the Apollo program was, the largest and most expensive ever. So it was a huge undertaking for many years, involving many people, and a lot of money. And at one point, it consumed about 5% of the whole U.S. federal budget. So the mission itself was pretty complicated. Probably these details. It was launched in several stages. First, getting off the Earth, and then most of it involved the command and lunar modules. And Buzz and Neil were actually on the moon only for 1 day in that very first mission. Later missions, they stayed on the moon for longer. But that first mission was only for 1 day. So it required, quite a bit of coordination between all these different stages and make sure everything worked. And the navigation system was one of the key parts of this. So the rockets are probably the thing most people are familiar with when they think about the Apollo mission. And even there, it was incredible. I think what they were able to accomplish. And even by comparing with today, the Saturn V rocket is still the largest and most powerful rocket. The closest is this SpaceX Falcon Heavy. But even there, it's still not quite the Saturn V. And one interesting thing about the Saturn V, if you notice the mass and the thrust numbers, if you convert that mass into a weight, you'll notice that the thrust was only just slightly larger than the weight. So that's why when you see the launch, you see when the rocket fires, it hovers there for a second, right? Because it can just barely overcome the weight of the rocket itself. Okay. Now, okay, then looking a little more closely at the rocket itself, you see that most of it looks empty, right? And that's because more than 90% of the volume was just fuel, right? Just to get it off the Earth. Now there was a guidance system on the Saturn V itself at the very top there, the stage, the third stage. That was designed by Bendix and built by IBM. But that's not the system I'm going to talk about. I'm going to talk about the system that was in the lunar module and the command module. And those had identical systems. And that also proved to be very important later for Apollo 13. Right? Because you remember that was when the command module was damaged and they had to use the lunar module essentially as a lifeboat. So the system I'm going to describe is essentially the same in both modules. This page is the most boring page, but I'll try and get through it fast. So the navigation system in the two modules was designed at MIT. There was a lab there called the Instrumentation Lab, which later became the Draper Lab. So many of you might know it better as that now. And one thing probably not many people know is that they actually had planned a mission to Mars before the moon mission. They had also done a lot of government work on nuclear missiles. So they had designed the navigation system and the computer for the Polaris nuclear missile. And that was one of the reasons they got the very first contract that NASA awarded for Apollo way back in '61. And that was because NASA realized that the navigation system would be one of the most difficult things to achieve. Then there was sort of a debate about what should be the best method, right? Some people were saying, we should use some sort of radio control. But remember, there was a race with the Soviets at that time, right? And there was some concern that if it was done by, radio, that it could be jammed by the Soviets. So at the beginning, they decided, let's focus on an inertial control system. And I'll explain how that works. The advantage of that system is it doesn't require any communication with the Earth. And then they also knew that because this was a very complex task, that you couldn't just have a person control the whole system, that they were going to need a computer. Now, if you think about what did computers look like in 1960, right? Most of the pictures you see are like these, giant mainframes, right? And now they wanted to put a computer on one of these, space systems. So the computer was also a very important part of the whole system. And it was the very first computer that used integrated circuits, not because they wanted to use the newest thing, but mostly they were forced to do that just from the size. Now, another story that you may have heard is that there were some problems with the computer on the landing. Some people tell the story as oh, the computer crashed when they were landing. It actually did not crash. It actually did exactly what it was designed to do. And I'll explain that later too. And then lastly, I don't know if any of you have worked on control systems or things like that. You may have, if you've ever used a Kalman filter, it's a pretty common thing in control systems. And the Apollo guidance system was the very first to actually use that. Okay, so this was the Mars mission that MIT designed before they worked on the moon mission, before there even was an idea to go to the moon. And this was sort of MIT's response to Sputnik. So after the Soviets launched Sputnik, the US was looking for, what could we do, so we can look impressive in the space program. And MIT came up with this idea of, what if we could send this probe to Mars, have it take some pictures and come back to the US, or come back to Earth and to deliver these pictures. So this mission never was approved, they never pursued it, but they did a pretty extensive study of it. And a lot of the elements that they developed for it did become part of the Apollo system. You'll see here, like there's some gyroscopes, there's a star tracker, all those were used in the Apollo system as well. Okay, so how does inertial navigation work? So this was the main navigation system at the beginning, although later radio control became the primary system, but for certain aspects of the mission, like for the moon landing itself, and also for the re-entry, and whenever the capsule went around the dark side of the moon, when there was no communication available, they had to rely on the inertial system. So it's based on just basic, freshman physics. So imagine you can measure the acceleration of the, of the system. So if you just integrate that twice, you get the position. That's it. It sounds pretty simple, right? But it actually involves a lot of details. First of all, you need to have, you need to measure the acceleration always with respect to the same reference frame. So that's why you need the gyroscopes as well, so that you can keep your accelerometers aligned always to the same absolute direction, right? And then the other challenge is both accelerometers and gyroscopes, they're never perfect, right? Like even if there's no acceleration, there might be some signal, and that offset can also drift over time. And because this mission was going to run for several days, they had to make sure that both the accelerometers and gyroscopes were very stable, over the whole length of the mission. Okay. Any questions on this part? Because this is actually sort of a key to the whole thing. No? Okay. All right. So this was the accelerometer that they used. So basically it was just a pendulum. So it was a cylinder. At the end of the cylinder was a very small mass, and then the whole cylinder would, just oscillate, just like a pendulum. And you can see in the cutaway here, the mass itself of the pendulum was just, to me, it looks like it's just a tiny screw here set in this groove. Now, you also have to isolate this whole thing from the environment in order to minimize the drift and other effects. So the way they did that was magnetically. So the cylinder was made of beryllium in order to keep it light, but then it was attached to these ferrite rods, and then there was these coils. It was suspended in these coils, and those coils were also what was used to drive the pendulum and also to sense the oscillations. And then the whole thing was suspended in a fluid. I don't know exactly what they used for the accelerometer, but probably it was the same as what they used for the gyroscope, which was some fluorocarbon. And the reason they kept it at a particular temperature was to try and balance the buoyancy of the beryllium cylinder. Okay. And here's another view of the accelerometer. So the the cylindrical part is the sensor itself, and then this was the electronics. So this was about the size of something that would fit in your hand, right? And this was only a single axis sensor. So it would just measure the acceleration along one direction. So then they would need 3 of these to get the X, Y, and Z. Okay, so that's the accelerometer. Now, they also, remember, you have to measure the accelerations all with respect to a given reference frame. So you have to make sure that your accelerometers are always oriented the same way. So that's why they needed the gyroscopes. The gyroscopes were even more complicated than the accelerometers. So it's, in a sense, it's like the classical, toy gyroscopes that you played with, those ones that you take and you pull a string and it spins. So in this case, it was also made of beryllium. NASA really loved this material because it's very light, and it would just spin about this axis. One of the things that was took me a little time to figure out was how did they actually make it spin, right? And how do they keep it spinning? Because you want this thing floating as well. So it was an interesting type of motor. It's not the most common motor you would think of. It was actually, there were no permanent magnets here. And I think the reason was Draper himself, who was in charge of the MIT lab at that time, hated permanent magnets. I don't know why, but I guess he felt that they weren't stable enough. So this is actually what's called a reluctance motor, right? There's no permanent magnets here. There's some steel rings here, and then you have these coils placed around it. And by pulsing the coils in sequence, you induce a magnetic moment on the steel rings, and then can make this thing spin. And then the whole thing was placed inside another beryllium sphere that was filled with helium. And that was mostly to keep the environment stable. They didn't want to expose it to air, especially with some of these, steel materials. They were worried about oxidation. And also another advantage of the helium, it has a lower viscosity, so it will create less drag on the spinning cylinder. And then that whole cylinder plus sphere assembly was also suspended magnetically, just like the accelerometer. So one side was the drive, and then another side was the sense. And then the whole thing, just like the accelerometer, the whole thing was floated in a fluid at a specific temperature to match the buoyancy of the sphere. Okay, here's a more detailed view of that. So the sort of dark blue part that you see in the middle, that's the cylinder that spins. And then the lighter blue that you see around it, that's the beryllium sphere that it sits inside of. And then there's a very thin film of fluorocarbon that it sits in. And then on either side, you have the magnetic suspension. And over here is a cross-section of an actual one. And you notice that this one, because it's been cut away and exposed to air, you see some of the parts have rusted here. And that was the reason that they, the actual one would be completely sealed with helium to avoid this. Okay. Then if you want to build your own gyro, you can. All this work is declassified now. So you can even get the machine drawings for all these elements, either from the NASA websites or other websites, right? So every little detail is here if you want to build your own gyro or accelerometer. So now those that I described, remember, were all just single axis accelerometers and gyros. So we needed 3 of each of those in order to sense all the directions. So here's how they were arranged. The accelerometers and the gyros, they were all placed in another beryllium block. And then there were these gimbals around to allow it to rotate. NASA used only 3 gimbals. There is one problem with this sort of arrangement. Like if any 2 gimbals become aligned, then you can't move around the other direction. So that's a phenomenon called Gimbal Lock. So it can happen in a real system. It can also happen if, I don't know if you've ever done any, tried to do rotations, transformations in, in just some simulation. You can also encounter this problem. Now, one way to avoid this problem is you could have the whole thing inside a 4th gimbal. But then that makes the system much larger, and NASA wanted to avoid that. So in the end, they just went with 3 gimbals. Okay. Then, I mentioned many times that they used beryllium. So you might think, like, when you're doing an experiment, like, hey, why don't we use beryllium here? And beryllium does have a lot of nice properties, right? It's one of the lightest metals. You can machine it, but it's also very dangerous, right? If you get these particles in your lungs, you will never get them out, right? So they had to, it requires a lot of care to do anything with beryllium. So don't use beryllium, even though NASA still uses it. Like, for example, I know on the James Webb telescope, this new telescope that's going to replace the Hubble Space Telescope, large parts of that are made of beryllium still too, but I would avoid it. Okay, so how good were the accelerometers and the gyros? So they had an opportunity to test the whole thing on the Apollo 8 mission. So if most people remember the Apollo 8, they remember it for this picture that you see in the background here. So it was the very first mission where they went all the way to the moon. They didn't land on the moon, they just flew around it. But it was a pretty bold mission. It was the first time that the astronauts actually flew on the Saturn V, and they decided to go all the way to the moon rather than just orbit the Earth. And part of the reason was that they had gotten some intelligence that the Soviets were about to launch a mission to the moon, and they wanted to beat the Soviets there. So during this mission, they had already switched the primary control system for most of the mission to the radio control, but they left the inertial system on just to collect data. So this is the data from the whole mission. And you can see at the top is the accelerometer data. This is ideally this should be 0 if you're in 0 gravity, but you see it's slightly, you can have, there's some offset, but as long as the offset is stable, you can deal with it, right? So that was the most important thing. They weren't so concerned about offsets, but it had to be very stable. And you can see that this is varying, to much, much less than, a milli-G. And then below is the gyro data. And notice the scale here. This is micro degrees per second, right? Over several days. This is pretty impressive, the stability that they were able to achieve. And then, so one of the reasons I, put all this information together was I was curious is like, how good are these Excel and gyros compared to what we have today with MEMS devices. And so I compared it to this MEMS device is a very high grade device. This is much better than you know, anything you would find in a cell phone, for example, today. It costs about $2,500, right? So this is a very high-end MEMS device. And what I'm comparing here is the key numbers are the bias error. So that's, remember, the how much off is it going to be from the actual value that you want. And also how stable is that over time. And when you look at those numbers, you can see that the Apollo IMU, even though it was designed more than 50 years ago, is still pretty impressive compared to, you know, even the best MEMS device that we have today. And I thought this was interesting because often you see comparisons of the computer. You know, there's a lot of people who will show you like, oh, this is what the Apollo computer was. And, you know, any computer in a cell phone today is much more powerful. But the sensors themselves were actually as good or better than anything we have today. Of course, they were much larger, but still, in terms of accuracy, they were pretty impressive. Okay, and now, you know, as I mentioned before, there's always going to be some drift in these sensors. So how do you essentially recalibrate them, right? I mean, you couldn't just fly them back to Earth and, you know, recalibrate them and continue the mission. You had to be able to do this while, you know, you're in space. So the way they did it was, you know, very simple, actually, in a sense. They just had a telescope. This is a view of inside the lunar module. Usually you see pictures from the outside, but here, if you see these triangular windows, those are the things that you normally see from outside. So the two astronauts would stand here on either side, and this was the door that would lead out of the module. And up here, they had a telescope. And with this telescope, they could see the stars, and they had a star chart, right? And there were certain stars that they had defined and to sort of span the whole ecliptic plane that they could see from at any point in the mission. And they used that to realign the IMU system. So there were 37 stars, and 3 of them they named for the Apollo 1 astronauts. You remember the Apollo 1 was the very first mission, but that was the one where the astronauts died in a test just on the ground caused by a fire in the command module. So they named 3 of the stars in their honor. So you can look through here and see if you can find them. Okay, and now this sort of system, you can still buy this sort of system from Draper. So this was the company, you know, the lab, the MIT lab that later became, you know, a separate lab. And they still make a celestial navigation system that you can buy from them. Okay. Then the other important part of the whole navigation system was the computer, right? So often you see comparisons of the computer to like what's the most powerful computer we have today. And of course, you know, anything we have today seems much, much more powerful. So I was more interested in looking like what's the closest equivalent to the Apollo computer. And probably many of you have used like an Arduino in your experiments. And it's actually pretty close to an Arduino in terms of the, you know, memory and processing power. So basically we went to the moon with an Arduino, right? Which sounds incredible to me. So then I want to talk a little bit more about each of the aspects of the computer. So as I mentioned before, it was the very first computer to use integrated circuits. And remember, this would be, okay, this would be like early 60s. Remember, the transistor was not discovered till 1947. So this is, a little over 10 years after the transistor was just discovered. And NASA decides to use this as a critical part of the whole space program. And at one point, NASA was consuming 60% of all the ICs made in the US. And so, I mean, NASA was really people don't usually associate NASA with, the development of integrated circuits. They were a big push in it. Now the ones for the Apollo, they tried to keep it relatively simple. There was just one design on these NOR gates for the computer, and then there was an amplifier also for the memory, but that's it. They wanted to keep it as simple as possible in order to guarantee the quality of the design. Okay, now the part probably you guys would be more interested in is the memory, right? That was all based on magnetics. So there were two types of memory, kind of like what we call the RAM and the ROM, but those terms didn't exist at that time. So the RAM is probably the type of memory you're more familiar with. It's what's called core memory. So basically you have these little ferrite rings, and you can either magnetize them, clockwise or counterclockwise, and that determines whether it's a 0 or 1. And then you do the writing and the reading just by stringing wires through these cores. And then when you pulse the wires, you pulse them with half the current that you need to overcome the coercive field. And so then only at that particular core that you want to switch, you'll get the writing. And then the reading is done essentially the same way. You pulse it the same way. And then you have another line that will sense the induced voltage. So because this is destructive, you have to rewrite the bits afterwards. Okay, and here's a picture of something from around the same time frame. This is not the Apollo core memory. This is from an IBM mainframe, but very similar. So you see the green wires are the ones for where you pulse it for the writing and reading, and then the red wires are the ones where you're doing the sensing. And it may look like in this picture, like it doesn't look like there's green wires everywhere, but they are. There's some of them are hidden behind the red wires. And this was the main type of memory for many decades. Like if you got any computer, this would be the type of memory that you had. There wasn't any solid state memory, until much later. And it's also, if you've ever heard the term, a core dump, this is where the term comes from, right? It comes from this type of memory. So that was the RAM, but now they also needed the RAM was relatively small. That could only hold like one program at a time for one particular aspect of the mission, but they needed many different programs for different parts, say for the landing versus the rendezvous versus the reentry. So they stored all that in a type of ROM. Now this was more interesting. This is not the type that you normally have heard of. This is called core rope. So even though the word is core, the information is not stored in the magnetization of the cores themselves. The information is stored by whether the wire is outside of the core or inside of the core. And I'll explain how that works. And here, if you look there's a picture of the Apollo computer. And the core rope modules are these, these like cards that would slide into the back. So they took up quite a bit of the volume of the whole computer. So let me explain how that works. Oh, here's a picture of them. And you can see they're very dense, right? That was another advantage of this core rope system. You could have multiple bits on each core, versus the core memory system where each core could only store 1 bit. Here you could run multiple wires and store many, many bits in each core. So let me explain how that worked. The first step of it was, okay, let's say you wanted to read the data on one of all the wires that are running through the core. So here I'm not showing the wires that are holding the information. What I'm showing you is the cores, and then I'm showing the wires that are going to do the addressing. So let's say we wanted to look at just this one. What we would do is essentially run a current that would saturate all the others, right? So what we would do is leave only the one core unmagnetized, and then the other cores would all be magnetized, okay? Then let's say there's another wire that would run through all the cores, you pulse this, and because the other cores are all magnetized, you won't induce any voltages through the data wires, right? Only in this one core that's not magnetized will you get these pulses, and then you sense them. So if the wire is going through the core, you'll get a larger pulse than if the wire is outside the core. So that's how you detect a 1 or a 0. Right? I know it's a little more complicated than the core system, but so this here I'm showing you just 3 wires in each core, but there were actually many, many wires. They could store many bits here through each core, but you would need 1 amplifier for each set of wires here. Okay. Then the other thing they had to figure out with the Apollo was how are the astronauts going to interact with the computer? Again, if you think about computers at that time, most mainframes use like punch cards, right? And probably some of you, remember using them yourselves, right? Maybe some of the first computer classes you ever took, you might have had to use punch cards, right? Obviously, they couldn't do that on the Apollo, so they had to develop really the first interface. And it was a very simple system. This they called it the disk key, which just stands for display and keyboard. They just would just show these numbers here, and then the astronauts would enter. You see here like verb and noun. So when they wanted to do something, they would enter a particular verb, and then a noun, to specify what it was that they wanted to do. I think I have a picture here. Okay, here's another picture of it. So for example, if they wanted to load a particular program, the verb for that was the number 37. And then to the particular program that they wanted to enter would also have a number. So the astronauts had some reference there for what all these meant. And then one that proved that was critical in that created these problems with the computer was this one that displayed the difference between the inertial system and the radio system. So this was something that they monitored during the landing. And this command here, this 1668, was the one that caused the problems with the computer during the landing. Okay, so let's hope this audio works. I'm going to try and play it from my phone because it didn't work before when we did it. So what you're going to hear here, this is a recording from Mission Control in Houston. And this is about, the astronauts have started the final descent to the moon. And you're going to hear three main voices, or three or four main voices. The first voice you're going to hear, which is a very deep voice, is Gene Krantz. So he's the head of Mission Control. He's the one who's most famous for saying, during Apollo 13, failure is not an option. So what he's going to do, he's going to go around the room and he's going to ask each of the people on the different systems, can we continue, right? And every one of those people could have aborted the mission. If they saw something was wrong, they would have stopped right there. And then the next person you're going to hear after they go through everybody is Charlie Duke. So he was what was called the Capsule Communicator. The astronauts could only hear him. And that was to avoid confusion, right? So he was the only one who could talk to the astronauts. Then you're going to hear some static for a while. And then you're going to hear Buzz and Neil, right? And this is where the first error occurs. Let me see. Okay, let's hope this works. So tell me if you can hear this. Okay.
Flight controllers, I'm going around the horn. Make your go-no-goes based on the data you had for an LOS. I see we got it back. Okay, retro, go. Fido, go. Guide, go. Control, go. Falcon, go. Go. Continue PDI.
Eagle, Houston, you're a go to continue.
Go at 4 minutes. Get that from
You're a go to continue power descent. You're a go to continue power descent.
Everybody, what does? Okay.
And Eagle, Houston, we got data dropouts. You're still looking good.
On the pings. Roger, I copy guidance. Okay, we got data back. Radar flight looks good. Raj. 2,000 feet. Raj, 2,000 foot elevation. We know any accepted guidance. Altimeter lights out. LH is minus 2,900.
Roger, we copy.
That's the Earth right out our front window. Houston, you looking at our delta H?
That's affirmative.
Program alarm looks good.
It's looking good to us.
Is accepting its guidance? 1202. Stand by. 1202. Looks like it's collision.
1202 alarm. Yeah, it's the same thing we had.
Right, retro. Go retro. Throttle down. 6 plus 2. Give us a reading on the 1202 program alarm. We're going that flight. We're going that alarm.
Roger, we got you. We're going that alarm.
Code when we go. Roger. He's taking it as up H now. Roger. Roger. 330. Did you get the
6
throttle
plus
down?
25, throttle down. 6 plus 25, throttle down.
Flight Fido, conversion on H. 6 plus 25. Flight control, we have velocity. Roger.
Okay, so everyone heard that? So now remember, this is just minutes from the moon landing, right? And Armstrong and Aldrin have done thousands of hours in the flight simulator, and now they're just they can see the moon, they're minutes away, and suddenly they see this error that they have never seen before, right? And so this is, you can almost hear in Armstrong's voice where he's getting impatient, right? He's asking them, what are we supposed to do here, right? And you notice that it only takes about, 10 seconds for Houston to respond and say, okay, you can continue, right? And how do they know that, right? And that's because when you look at that control room, you see, those few dozen people there. What you don't see is behind them, there's hundreds of people who are supporting each of those key people there that you heard at the beginning. And during one of the simulations, there was some other error that popped up that they had never seen before. And Gene Krantz told the engineers, I want you to go through every line of code and figure out what do we do when that error comes up. So that's why they knew that they could continue. But now this was not the only error that occurred, right? There were 4 more errors that occurred over the next few minutes, but each time, you know, Houston cleared them and they continued. Whoops. Okay, so of course they made it to the moon, right? And then once they landed on the moon, the first thing that NASA did was call up MIT and say, hey, you guys need to figure out what caused this error. Because remember, they only had 1 day on the moon, and they didn't know, would this cause a problem when they tried to leave the moon? So MIT worked very hard to try and figure out what was producing this error. And it turned out what it was the Rendezvous Radar, right? So this was a system that was used when they left the moon for the lunar module to connect back up with the command module, right? And the astronauts had turned on the system in case they needed to abort and go back to the command module. But what was happening was this rendezvous radar was sending data to the computer, and it was overloading the computer. And so what the computer was doing, it was restarting in order to clear out the queue of all the jobs and focus on just the navigation, right? So the computer was actually doing exactly what it was supposed to. It was just the astronauts hadn't expected it. And actually for the last 2 errors, even the display went blank. And then afterwards, after the mission, when they debriefed Armstrong, they asked him, well, why did you keep going, right? And he said, well, it looked like the ship was still responding, right? So in the end, it was the right decision. And it was sort of the foresight of the MIT team that designed it to be able to handle even these cases that they hadn't expected. Okay, so they made it, and they made it back, and the navigation and inertial system was very important for the reentry, because during the reentry, remember when it's going through the atmosphere and it creates this plasma around the module, they can't communicate with the Earth. So the inertial system was very important for that too. And then they were picked up by the USS Hornet. And if you come to California, you can actually see this here. It's still here. And they have a nice exhibit about the Apollo 11 mission. Okay. And then remember at the beginning, I promised to explain to you where's the navigation device in that picture. So if you look very closely, you can see the astronauts were always wearing a watch, right? And this watch was sort of their ultimate backup system. And it proved to be pretty important in the Apollo 13 mission as well. Because there were several other systems failed, they had to time some of the maneuvers basically with their wristwatch. Right? You can still buy this watch if you like, although it'll cost you several $1,000s. Omega still makes it. Okay. And then lastly, I have a bunch of references here that you can, if you want to learn more. The one in particular I'd recommend is this podcast from the BBC, 13 Minutes to the Moon. That was the one that I was listening to that I first heard about the navigation system. They have 2 seasons. The first season is about Apollo 11, and then the second season is about Apollo 13. They're both excellent. And then it's sort of interesting to look back at, like, you know, what did we accomplish before Apollo and after? And one of the things that struck me was like the time between, you know, the first airplane and the moon landing was only 66 years, right? I mean, we're already now almost 52 years since the moon landing. So it's pretty incredible that, you know, we went from the first airplane to the moon landing in just that time. And another interesting fact is, all the astronauts got to carry some personal item with them to the moon. And one of the things that Neil Armstrong carried was a piece of the Wright Flyer. The Smithsonian, I think, had given him that, and he took that all the way to the moon. And then lastly, you may wonder, what was I doing when this was going on, right? I was training to be an astronaut, of course. This is a real picture, so there was no Photoshop at that time. Okay, so that's all. I don't know how to get out of this right now. So any questions?
Thank you very much for your fantastic talk. And we have a question, just a moment. Thank you for such a nice talk, Savas. I'm wondering if you have any idea of how many magnetic sensors were there on the system and how many you assume there are now.
How many magnetic sensors there were on
Yes.
the Apollo? Let's see. So the accelerometers and the gyroscopes all used magnetic sensing, right? That was how the actual detection of the motion of the accelerometer or the gyroscope was done magnetically. And I think in addition to that, I think they had some magnetometers just to measure the fields in space. Today, I don't know. I know they use, I don't think they use magnetic sensing for the accelerometers and gyroscopes. I know like for the gyroscopes, they have like these ring gyroscopes. They use lasers. So I think it's an optical detection system. But NASA still does a lot of work on measuring the magnetic fields in space of different planets as well. So there's almost always a magnetometer on every mission.
Okay, thank you. And is there any question more?
And any what?
Any question?
Oh, any more questions?
If you have any questions, just open your mic and pose your question.
Maybe hi Savas. I didn't fully understand the rope memory. So where's the information? Because I think each bit is one ring, and how can you multiply this by just putting more wires into the same rings? Okay,
let me explain this a little more. So the bit is not the ring.
Not?
No, not in the core rope. So remember, there's two types of memory. There's this one, the RAM. So there you are magnetizing the core in one direction or the other.
Yes, yes.
And that's the traditional one that probably you've heard of before. But the core rope is different. So the information is not stored in the magnetization of the cores. The information is stored by whether a wire is running through the core or outside the core. And then the core is just used for addressing.
But how can you change the information? I mean, you cannot take the wire out from in to out. Or...
Right, exactly. Yeah, so this is the ROM. So this is where they stored the programs.
The ROM. Okay. I see. Yes. Yeah, okay, thanks. Yes. That was my misunderstanding. Yeah, okay.
Yeah, I should have emphasized that. Yeah, so this is a perfect system where you can't possibly get a bit flip. Right?
Yeah, yes.
There's no way for the wire to jump from outside to inside, right? So it was also perfectly radiation hard.
Yes. Okay, yeah, thank you.
It is a very, very clever
Yeah, it's pretty impressive. What
Do
they're
you have
able
an idea of the size of one ROM?
here you can is a picture of the Apollo, the whole computer, and you see these ROM modules are these like things that slide into the back. And each of the cores, they're fairly big. You know, they're about 9 millimeters or so. Got a picture of it here. Okay. But there were, you know, like hundreds of wires running through each of these cores, right? So you can imagine it took a long time to make this, but once you made it, then you could be absolutely sure that it would never change.
And if there was an error, then you
yeah, you'd have to start from the beginning.
Yes.
There's no way really to fix it.
And for the round, do you have an idea how the harsh environment would influence either you have a 0 or a 1? If that was, I assume it was really important, like to take care of temperature and the pressures, and then you talked about some very harsh reagents or materials in the system.
So the RAM was this ferrite. Right? So I think once that was magnetized, I think it was pretty stable, at least over the time period that they would need to run the program.
Yeah, but do you have an idea of if it was important at that time, at least the conditions and how they overcome that?
I don't actually know like what type of, you know, radiation testing they did. But I know these ferrite cores are pretty big. And I think once they're magnetized, it's not as easy to flip as say, you know, I don't know, solid state memory now, where each bit is like maybe tens of electrons, right? That I think is much easier to flip. I think this was relatively stable.
You go ahead, Diana, just talk.
Hi, I just didn't want to interrupt. So first, thank you for the very nice talk. I have more of a curiosity because this was a very interesting overview of technology that I speak for myself. I'm not very familiar with. But now in the SpaceX program, what are the parallels between this technology and what is being considered for the next, in this case, the Mars mission? Are they the same? Are they very different? Of course, technology has evolved a lot, but this technology is very robust, as you said. So what are the new paradigms or the new shifts that were really, really relevant for these technologies, let's say like this?
So I know almost all even the current missions have some degree of inertial control. Right? So that is still a key component of many systems. Because like I said at the beginning, it's the only navigation system that doesn't rely on any sort of external communication. So if you lose contact with, you know, the ground or with the GPS system, then you have to rely on something
you're safe, right?
Internally, right? And the inertial system is the only one that can do that. The things that have changed, of course, are the sensors themselves. So they've improved a lot. So like I said, for the gyroscopes, I don't think they're using, you know, these gyroscopes, which are just spinning tops. They're using like ring lasers and other more sophisticated things, but they're still not using, say, MEMS sensors. MEMS are what you find in most commercial devices. Those are not quite good enough yet for long, like space missions. But maybe, I don't know, maybe in another decade, they'll become better. Yeah.
I have have a question. Do you have any idea? Can you hear me?
Yeah, I can hear you.
Do you have any idea? I mean, it must be, my feeling is that it must be much cheaper now in terms of, if you look at equivalent dollars between like, let's say at the time of Apollo 11 and what it costs to send a rocket up into space now. Do you have any idea about that?
Yeah. Here.
Oh,
Okay.
it's there. Okay, I didn't.
Yeah, so you can see like how much a Saturn V rocket costs.
Okay.
Versus a SpaceX rocket. And of course, they can reuse parts of that as well. I don't know if that was factored into this cost here.
Right, because you can take it up again, right? So,
right.
Yeah. Okay, thank you.
Just out of curiosity, because we always think that we evolve in technology and then the old technology gets behind. I'm just reading a NASA tweet from Aung Chancellor, which is an expert that was in the space station, and she was experimenting a sextant. So it was used on the 15th century for the navigation with boats. Yeah. So they really think of everything.
Yeah, and that is another thing that is still used, right? Because again, if you lose contact with the ground, right, it's your one absolute reference.
Any other question? No? Mustafa? No?
No, any more question? Again, thank you very much, Savas. It's very fantastic talk, and it's nice to see you again.
Yeah, nice to see you too.
Thank you. Thank you very much.
Thank you.
Okay. Thanks a lot. Glad you enjoyed it.
Yeah. I just want to take this opportunity to say that in our website, you can also find PhD positions that are open until the end of this month. And make sure you check what we are doing on our website, because we always have some new things going on. Okay, so see you in 2 weeks for the next seminar. And thank you again, Savas, for accepting this very nice invitation and for this really great talk with science and also with this history.
Thanks. Can I apply for those PhD positions too?
Of course you can. And then for years with us, that would be awesome.
Bye-bye. Have a nice weekend.
Bye.
Bye.
Thanks. Take care.